We have already learned about rational numbers and irrational numbers. We looked at rational numbers as ratio of two integers where denominator cannot be zero, and we see that irrational numbers cannot be expressed as the ratio of integers. There is another way to represent these numbers called decimal representation. Let's look at that. Here we have some simple rational numbers. Let's convert them into decimal using long division. First, look at 1/2. We divide 1 by 2. Since 1 is smaller than 2, so we take decimal and take 1 0. 2 times 5 is 10. We have 0 remainder. So 1/2 is equals to 0.5. Let's see 1 over 5. We divide 1 by 5. Here again 1 is smaller than 5. So we use decimal. We take 1 0 here and 5 times 2 is 10. So again here remainder is 0. Here in both examples we have seen that our division terminates, meaning the division stops after a few decimal places because our remainder becomes exactly 0. Now let's see more rational numbers. 1 over 3. Let's divide 1 by 3. So 1 is smaller than 3. So we take decimal and bring 1 0 here. 3 times 3 is 9. We have remainder 1. Again 1 is smaller than 3. So we take another 0. And 3 times 3 is 9. Again remainder 1. Again we take 0. And 3 times 3 is 9. We are stuck in a loop. No matter how many times we try this division, it will never end. So 1 over 3 is equals to 0.333333 and so on. 3 infinite number of times. But notice that even though it never ends, there is a perfect pattern. The digit 3 just keeps repeating forever. Let's look at another rational number, 5 over 11. Let's divide 5 by 11. Since 5 is smaller than 11, we take decimal and we take 1 0 here. So 11 times 4 is 44. We have 6 as remainder. Again 6 is smaller than 11, so we bring another 0, and 11 times 5 is 55. So again here we have 5 remainder. Again 5 is smaller than 11, so we bring 1 0 here, and 11 times 4 is 44. We have 6 remainder. Again 6 is smaller than 11, we bring another 0, and 11 times 5 is 55. We have 5 as remainder. Again you can see here we are in a loop, but this time the digit 4 and 5 repeating together in a cycle. So 5 over 11 is equals to 0.454545 and so on. To make writing these infinite loops easier, we have a special notation. For the repeating part, we write a horizontal bar above the repeating number. So here 0.33 is written as 0.3 and a bar above 3, which is representing that 3 is never ends, it's just repeating. Here in 5 over 11, the digit 4 and 5 are repeating. So we can write 0.45 and a horizontal bar above the repeating digits 4 and 5. So we have seen 1 over 2 and 1 over 5. These numbers are terminate, means their decimal representation ends. But these two numbers, 1 over 3 and 5 over 11, their decimal representation do not terminate but repeat. So, if we convert any rational numbers into decimal form, there are only two possibilities. Either that decimal terminate or non-terminate but repeats. But doesn't it make you wonder what makes some rational numbers to terminate and others to non-terminate but repeat? Is there any hidden patterns? Let's find out. Here we have a few simple terminating rational numbers. Note that all these fractions are terminate beautifully, but look closer at their denominators. 10, 20, 4 and 25. Did you know we can write every single one of these denominators as power of 10 using equivalent fractions? Let's see. 1 over 10, here denominator is already in the power of 10. 3 over 20. So as we have discussed in our earlier videos, that we can multiply any rational number with non-zero integers both in numerator and denominator, that will gives us equivalent numbers. So here we can multiply 5 both numerator and denominator, and the number we got 15 over 100 is equivalent to our previous number 3 over 20. So here our denominator is in the power of 10. Look at 1 over 4. Here we can multiply numerator and denominator with 25, and we have 25 over 100. Here too our denominator can be written as power of 10, 1 over 25. Here we multiply 4 both in numerator and denominator. We have 4 over 100, which is equals to 4 over 10 to the power 2. Here too our denominator can be written as power of 10. Every terminating denominator can be scaled up to a power of 10. But why is this possible? Because the number 10 has only two prime factors, 2 and 5. This means any denominator made up of only 2's, 5's or both can always be scaled up to a power of 10. Let's check our denominators. 3 over 20. Here denominator is 20 and its prime factors are 2 times 2 times 5, which is 2's and 5's. In 1 over 4, denominator is 4. Its prime factors are 2 times 2. Here only 2's, fraction of 1 over 25. Here denominator is 25 and we have 5 times 5, only 5's. These are all rational numbers whose decimal representation terminates. Let's look at some more examples. We have already seen that decimal representation 1 over 3 does not terminate. So here denominator is 3 and its prime factor is 3. 1 over 6. Its decimal representation also non-terminating and repeating. So its denominator is 6 and its prime factor is 2 times 3. So if we have a simplified fraction, we look at its denominator, we do its prime factorization. If factors are only 2, 5 or both, then decimal representation of that rational number terminates. But if prime factorization of denominator has other factors like 3, 7 or 11, then that rational number do not terminate but repeats. So here we have a question, decimal representation is terminating or non-terminating and repeating. So we look at its denominator, which is 15, and we write its prime factors. 3 times 5. As we have discussed, if denominators have prime factors other than 2 and 5, then that rational number has non-terminating and repeating decimal representation. So because of 3, we write that it is a non-terminating and repeating. If you do it as it is, you get 0 number. Why it is? Because this fraction is not in its simplest form. We have to first convert it into its simplest form, then we look at its denominator. Okay, so we follow 2 steps. Step 1 is to convert this fraction into simplest form. 3 over 15 is equals to, we write prime factors of both numerator and denominators. 15 is 3 times 5. We cancel out common terms and we have 1 over 5. So 3 over 15 and 1 over 5 both are equivalent. Now in step 2, we look at prime factorization of denominator. So we have 1 over 5, its denominator is 5, which have prime factors only 5. So we know 3 over 15 is a terminating rational number. So here we have another question. We have a rational number 6 over 45 and the question is whether it is terminating or non-terminating and repeating. So let's solve it. So our step first is to convert this into its simplest form. So 6 over 45 is equals to, we write prime factors of 6 and 45. Prime factors of 6 is 2 times 3 and prime factors of 45 is 3 times 3 times 5. So we now cancel out common terms. So we have 2 over 15. Now move to our second step. We look at denominator of our simplified rational number. So here denominator is 15 and its prime factors are 3 and 5. So denominator have 3 as a prime factor. So 6 over 45 is non-terminating and repeating. Unlike rational numbers, which either terminates or repeats their decimal digits, irrational numbers have decimal representation that never terminates, meaning they go on forever, and they never repeat a pattern, meaning they are non-recurring. Let's see some examples. Square root 2. Its decimal representation is 1.4142 135623730950488 and so on. Another irrational number, which is pi, its decimal representation is 3.14159265358979 and so on. No matter how many millions of digits you calculate, they will never end and they will never settle into a repeating loop. So in many calculations, we use pi is equals to 22 over 7, but we have learned that pi, which is an irrational number, cannot be written as ratio of integers. So how can it is written here 22 over 7? Pi is not equals to 22 over 7. Actually, it is just an approximation. Actually, 22 over 7 is a rational number, not an irrational number. We have seen that 1 over 3 is equals to 0.3333 and 3 is just repeating. If we look at 1 over 3 inside a calculator, we see that there is a finite number of 3's. But as we know, 1 over 3 has a repeating 3 which never ends. So here we can see that calculators have their own limitation. They display some finite number of digits. So what we have seen is that decimal representation of rational numbers is either terminating or non-terminating and repeating. And decimal representation of irrational numbers are non-terminating and non-repeating. This is homework question for you. Write your answer in the comment section.